Electrochemistry is the last unit that we're going to cover, or the last part of this unit. It won't take very long. And so we have to define a couple of things. First of all, we should probably define what electrochemistry is, which happens to be the relationship between chemical change and electrical work. Electrochemical cell is another thing that we are going to be spending a lot of time working with in terms of problems and things like that. And that's a system that uses redox reactions to make or use electricity. Some of you really, really loved the redox unit earlier, so we're going to go back to that for a bit. There are two types of electrochemical cells that you're going to be responsible for understanding. The first one is the voltaic cell. The second one is the electrolytic cell. The voltaic cell uses thermodynamically favored redox reactions that release energy to produce electricity. And the electrolytic cell uses electricity to drive a redox reaction that's not thermodynamically favored. We are going to really spend a lot of time in the voltaic cell, but we will definitely touch upon the electrolytic cell as well. So at one point or another last year, we did a demonstration for you guys where we took a nail and we put a nail in copper sulfate, which is the blue liquid that you're looking at here, and we let it sit for like a big chunk of the hour, and then we came back at the end of the hour and we had the rust appear, okay? And then you guys did a lab where you took a piece of copper coil and you put it into copper sulfate, into silver nitrate rather, and when you put it into silver nitrate, you let it go for a while, like a whole night, and then you came back the next day and you were able to knock off all the silver and you had produced the silver. So those are the types of reactions that we're kind of talking about here when we talk about electrochemistry. The example that's up here is the fact that we have copper sulfates, or well, a copper chloride or a copper sulfate or a copper nitrate solution. It doesn't really matter because whatever the anion is a spectator ion. And then we have, in this case, a piece of zinc that is being stuck into that particular solution. Now, the zinc is the solid part. So in the blown up section right here, this would be my zinc, and the copper ions would be floating around in solution. Over time, though, because this reaction happens to be thermodynamically favored, what ends up happening is the zinc and the copper switch places. But more specifically, what happens is that the zinc, which is solid, and as a result of it being solid is not an ion, becomes an ion by doing what? It's a +2, so what happened? Did it gain or lose electrons? It lost electrons, right? And so then the copper ion that was in solution now has some electrons that it could pick up, and so it picked up a couple of electrons, so it gained electrons to become copper solid. So in this particular scenario, this layer right here is equivalent to that black stuff right there, okay? So what I'm getting at here is that in a thermodynamically favorable electrolytic or electrochemistry reaction, we actually have a single replacement reaction occurring a lot of the time, okay? So to go back to redox reactions, we should probably review them a little bit, and we should probably be able to go ahead and balance this, but I think that we'll do it as a team, and just to kind of refresh your memory, because last hour some people remembered, but then they forgot, and then they remembered again. So the first thing I'm going to do is I'm going to write the half reaction. So I'm going to say I have BH4, which is a -1, reacting to form H2BO3, also a -1. In this case here, it appears that my borons are balanced, so the only things are left to balance are the hydrogens and the oxygens, and we balance the oxygens first by adding water. So I'm going to add 3 waters over here, which will give me my balance of my oxygens. So on the product side, or the right-hand side, I need to add, what is it? Let's see. I have a grand total of 10 hydrogens on the left side. Do you see that? And 2 already on the right side. So I'm going to go ahead and add 8 hydrogens over here. Okay. And so at this point here, on the left side, I have a -1 charge, and the right side, I have a +7 charge. So I need to get them to a -1. So I'm going to add 8 electrons here. So far, so good. Then I'm going to write the second half reaction, which in this case is ClO3 minus 1, and the chloride ion. And again, my chlorines are balanced, but my oxygens are not. So I'm going to go ahead and balance them, the oxygens, by adding water. In this case, I'm going to add 3 waters, which will give me 6 hydrogens. So I need to add a total of 6 hydrogens over here. Now I need to assess charge, and on the right side I have a -1 charge, and on the left side I have a +5 charge. So I need to add 6 electrons here to make it get to a -1. So far so good with that. Okay, so now what I'm going to do is I'm going to multiply this reaction by the lowest common multiple of the number of electrons, which the best I can tell is what, 24? So I'm going to put a 3 here. So down below I'm going to have 9 waters and 3 BH4s and 3 H2BO3s and 24 hydrogens and 24 electrons. And then what I'm going to do is I'm going to go ahead and multiply the bottom or the secondary reaction by, again, we're trying to get to 24, so I'm going to multiply this by 4, which will give me my 24 electrons, my 24 hydrogens, my 4 ClO3s, my 4 Cls, and what is that, 12 waters. Now I'm going to go through and cancel out things I can cancel out. I'm going to start with my electrons. Those cancel out completely. It also so happens that my hydrogens cancel out completely. And when I'm looking at waters, I can get rid of 9 waters here, 9 waters here, and be left with 3 waters here. So when I rewrite this reaction all together, I'm going to take the 3BH, oh boy, the 3BH4 minus 1 plus the 4 ClO3 minus 1 makes the 3 H2BO3 minus 1 and the 4 Cl minus 1 and the 3 waters. So that's my balanced half reaction down here. Now, this says that it's in basic solution, which means that if there were hydrogens, I'd have to add what now? OHs to both sides. But because there are no hydrogens present and everything is balanced in terms of charge, I don't have to add any, so we're just going to leave it as it is. Now, the other thing that it asks you to do is identify the species undergoing oxidation and the species that happens to undergo reduction. So to go ahead and figure that out, I am going to go ahead and look at the boron. So I know that I have hydrogen here, so I have, let's see, what is it? Plus 1 times 4, which gives me a plus 4, but we need to get this to a minus 1. So the boron in this case has to be a what, plus 5? Or minus 5 rather? Yeah? Okay. Then I have my chlorines, and so we know that the oxygen in this case is a minus 2 times 3, so that's a minus 6. So the chlorine, in order to get to a minus 1, has to be a plus 5. Hydrogen in this case is a plus 1, and I've got 2 of them, so it becomes a plus 2. Oxygen is a minus 2, and I've got 3 of them, so it becomes a minus 6. We want this to be a minus 1, so the boron has to be a what then? Plus 3, right? It's got to be a minus 1. Correct? And then over here, the chlorine is a minus 1, so it's just a minus 1. So what's happened here in terms of the chlorine versus the boron, right? Well, the boron was a plus 5 and became plus 3, and the chlorine was a positive 5 and became minus 1. So we'll come back to that. In this case, what happened to boron? It was a minus 5, and it became a +3. So what did it do? It lost electrons, right? And then what happened to chlorine? It was a +5 and it became a -1. So what did it do? Gained electrons. So that means that in this case, boron lost, so loss of electrons is oxidation. Oh boy. And chlorine gained, so that became a reduction. Any questions about that? The timing on that is good because this is where I'm going to stop. Your homework is due 2018, 2025, just C and D. Have a wonderful day. We'll see you tomorrow. Just to review, we have oil rig or Leo goes GER, whichever one you feel more comfortable with. But oil rig says oxidation is a loss of electrons and reduction is a gain of electrons. Whereas Leo goes GER says it's a loss of electrons is oxidation and gain of electrons is reduction. Remember, what?
Can you go back?
I'm going to. Hang on. Oxidation involves a loss of electrons. Reduction involves a gain of electrons. And new this year, you don't have to anymore identify what the oxidizing agent is or the reducing agent, which is what we did talk about that the first time around.